In 1980, Voyager 1 sent back an image of a small moon orbiting Saturn, and astronomers immediately noticed something strange. They had seen that shape before. 3 years earlier, Star Wars had introduced the Death Star, a fictional moon sized weapon dominated by a massive circular dish. Mimas had almost the same unsettling geometry, except nature had built its version first. The resemblance comes from Herschel Crater, an enormous impact scar covering roughly one-third of the moon's diameter. At its center rises a peak almost 4 miles high, taller than any mountain in the lower 48 states. But the crater creates a much bigger problem. The collision that formed it came dangerously close to destroying Mimas completely. Shock waves traveled through the moon hard enough to fracture terrain on the opposite side. Somehow, Mimas survived. For decades, that battered surface seemed to tell the rest of the story. Scientists considered Mimas frozen, geologically inactive, and relatively simple. Then they measured its movement. Mimas wobbles as it orbits Saturn, and measurements of that wobble eventually pointed towards something difficult to reconcile with a completely frozen interior. In 2024, researchers presented evidence that beneath roughly 12 to 19 miles of ice could be a global liquid water ocean, potentially young on geological timescales. A moon famous for looking like a fictional weapon may be hiding something far more consequential beneath its surface. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's start with the small frozen moon Voyager, revealed in extraordinary detail. Against the enormous scale of Saturn, Mimas occupies a narrow path close to the planet, moving through a region dominated by rings, gravity, and ice. It is the smallest and innermost of Saturn's major moons, only about 246 miles across. Saturn now has 285 confirmed moons, yet Mimas remains one of the classical satellites that first revealed how complex this system truly is. Its place in human astronomy began on September 17th, 1789. William Herschel found it using his 40-foot reflecting telescope in England, then the largest telescope ever constructed. At that distance, there was no cratered world to admire through the eyepiece. Herschel saw only a faint point moving where fixed stars did not. The name arrived later through Herschel's son, John Herschel. He chose Mimas from Greek mythology, drawing from the family of giants associated with the ancient struggles of the gods. That mythological identity eventually became attached to a world no human eye had yet seen clearly. Its greatest surface feature would later receive another family connection. Herschel Crater carries the name of William Herschel himself, permanently placing the discoverer on the moon he first detected. Mimas circles Saturn at an average distance of roughly 115,000 miles from the planet's center. Our own moon travels more than twice that distance from Earth. Here, orbital motion is rapid. One journey around Saturn takes only 22 hours and 36 minutes, meaning a complete Mimas year passes in less than one Earth day. That orbit also controls how the moon turns. Mimas is tidally locked, a condition in which its rotation matches its orbital period. The result is familiar to us because Earth's moon behaves the same way. One hemisphere continually faces Saturn, while the opposite side looks outward as the moon travels around its enormous primary. The environment is brutally cold. Surface temperatures can sink below minus 300 degrees Fahrenheit, and the landscape is dominated by water ice. Its low density supports the same picture. Mimas is largely ice, with a smaller contribution from denser material deeper inside. For generations, the surface seemed to complete the story. Craters cover almost every available region, preserving impacts rather than being erased by widespread resurfacing. To an astronomer, such terrain traditionally signals great age and little geological renewal. Yet Mimas does not simply accompany Saturn, its orbit participates in the architecture around it. Gravitational resonance, a repeating orbital relationship that allows small gravitational pulls to accumulate, gives this modest moon influence far beyond its size. From its position beside Saturn's rings, Mimas helps organize material spread across distances vastly greater than its own diameter. So when you picture Mimas in its proper setting, you are seeing more than an icy satellite. We are looking at a small world bound tightly to a giant planet, moving rapidly through a gravitational system where even a moon only a few hundred miles wide can leave a lasting physical signature. A crater usually records damage to a world. Herschel records something closer to the boundary between damage and destruction. Its circular rim spans roughly 86 miles, consuming more than one-third of Mimas from edge to edge. On a moon this small, the structure dominates the landscape so completely that its scale becomes difficult to separate from the moon itself. Imagine the same proportions transferred to Earth. A comparable scar would stretch across much of the United States, reaching roughly from New York City toward Denver. Yet width tells only part of the story. Portions of Herschel's floor descend around 6 miles beneath the surrounding terrain. Along the rim, enormous walls preserve the excavation left behind when the surface was driven downward and outward. At the center stands something stranger. A mountain rises roughly 4 miles from the crater floor. It formed during the final moments of the collision, when immense pressure temporarily changed how solid material behaved. Under those conditions, ice and rock can deform almost like a very thick fluid. The compressed surface rebounded upward after the impact, lifting material into a central peak before everything hardened into place. The object responsible may have been roughly 6 miles across. That places it within the broad size range of the asteroid associated with Earth's end Cretaceous mass extinction. But Mimas offered a vastly smaller target, with far weaker gravity and far less material available to absorb the collision. Impact simulations reveal the difficulty. An event capable of excavating Herschel approached the amount of energy needed to disrupt Mimas completely. The incoming body struck fast enough to drive a powerful shock wave through the moon's interior. Material near the impact site was crushed, fractured, heated, and accelerated outward. Some escaped Mimas altogether. The disturbance did not remain near Herschel. On the hemisphere opposite the crater, researchers have identified fractures and grooves that may record stresses transmitted through the entire moon. A shock wave could have crossed the interior, converged on the far side, and broken the surface there. You can trace the possible aftermath across a world only a few hundred miles wide. Why did anything remain? That question depends on details we cannot reconstruct perfectly. Impact velocity matters, so does angle, internal porosity, ice strength, temperature, and the structure Mimas possessed when the collision occurred. A porous interior can absorb energy differently from a compact one. Ice also responds differently depending on pressure and impact speed. Computer models suggest Herschel formed remarkably close to the catastrophic disruption threshold, where an impact leaves a gravitationally scattered collection of fragments instead of an intact moon. Yet Mimas remained coherent enough to continue orbiting Saturn. Its survival therefore preserves a narrow physical outcome. The impact was powerful enough to reshape a substantial fraction of the moon, send stress through its interior, and raise a mountain from compressed material. A little more energy might have erased the world carrying the crater. 3 years separated two images that would eventually become inseparable. The first belonged to fiction. In 1977, Star Wars: A New Hope introduced audiences to the Death Star, a spherical battle station whose surface contained an enormous circular superlaser dish. Nothing about its design was intended to represent a moon of Saturn. Then Voyager 1 reached the Saturn system. On November 12th, 1980, the spacecraft made its closest approach to Saturn and returned detailed photographs of Mimas. Once the images were processed, the resemblance was difficult to ignore. A spherical world filled the frame, and across one hemisphere sat Herschel Crater, positioned like the circular weapon dish on the fictional station. The timing made the coincidence especially unusual. George Lucas and the artists responsible for the Death Star had created their design before close spacecraft images revealed Mimas in recognizable detail. There is no evidence that the moon inspired them. The similarity emerged independently, with planetary geology producing a shape that cinema had already imagined. Look closely, and the comparison becomes more specific. Herschel presents a broad circular basin surrounded by a raised rim. Near its center rises the prominent peak left by the impact. Seen under suitable lighting, those elements create the same basic visual arrangement as the Death Star's recessed superlaser assembly. Yet, the resemblance comes from ordinary physics operating under extraordinary conditions. Large impact craters often develop central peaks during the final stages of formation. Extreme pressure compresses the target material, forcing ice and rock to deform for a brief interval. When that pressure falls, material beneath the crater rebounds upward. The motion freezes into place, leaving a mountain near the center of the basin. You can find related structures elsewhere. Large craters on Earth's moon contain central peaks. So do craters across Mars and Mercury. Gravity, impact velocity, target composition, and crater size alter the final result, but the underlying process remains recognizable across different worlds. Mimas simply presents that geometry with remarkable visual clarity. The comparison became so persistent that the National Aeronautics and Space Administration has used Death Star language in public material about Mimas. A scientific object acquired a second identity through popular culture, allowing an icy moon hundreds of millions of miles away to become recognizable before many people ever learned its name. There is something useful in that resemblance. Human beings often associate symmetry and geometric order with deliberate construction. Circles, centered structures, and repeated proportions can appear engineered because our own machines use similar forms. Nature has no need for an architect to produce them. Impact physics can organize shattered material into rings, basins, rims, and peaks through mechanical laws alone. When you look at Mimas and see a manufactured object, you are also seeing how readily natural processes can create forms that our minds interpret as design. From Earth, Saturn's rings seem almost perfectly ordered. Through a modest telescope, however, a dark band separates the bright inner B ring from the outer A ring. This feature is the Cassini division, first recognized in 1675 by Giovanni Domenico Cassini. Its existence reveals how gravity can shape matter without ever touching it. The division spans roughly 3,000 miles. Early observers naturally interpreted the dark region as empty space, a clean break between neighboring rings. Modern observations show something subtler. Particles still orbit there, but their concentration is far lower than within the brighter rings surrounding them. Mimas plays a major role in creating that difference. The mechanism is orbital resonance, a repeating gravitational relationship between objects whose orbital periods form a simple numerical pattern. Near the outer part of the Cassini division, ring particles complete roughly 2 journeys around Saturn during each orbit made by Mimas. Astronomers call this a 2-to-1 resonance. A single encounter accomplishes almost nothing. Mimas is small, and its gravitational pull on an individual ring particle is weak, yet timing changes everything. Imagine giving a playground swing a tiny push at precisely the right moment. One push barely matters. Repeated at the correct interval, each addition builds upon the previous motion. Orbital resonance follows a related principle, except gravity supplies the recurring influence. As resonant particles circle Saturn, Mimas repeatedly perturbs their paths. Those small changes accumulate. Their orbits can become more eccentric, meaning less perfectly circular, allowing interactions and collisions to redistribute material away from the resonant region. Across immense spans of time, a subtle gravitational rhythm becomes visible structure. You can actually see its consequences from Earth. This makes Mimas unusual in scale. The Moon itself is modest beside Saturn, yet its gravitational timing influences a ring feature thousands of miles across. No physical barrier marks the division. There is no wall preventing particles from entering. The architecture emerges from orbital motion and repeated gravitational encounters. Mimas is also only part of the story. Other resonances and moons influence Saturn's rings, producing edges, waves, gaps, and narrow structures throughout the system. Some moons even orbit within gaps and help maintain them directly. Resonance extends far beyond Saturn. Jupiter creates related gaps within the asteroid belt. Moons can lock into repeating orbital patterns with one another. Entire planetary systems around distant stars may settle into chains of resonances that preserve recognizable arrangements for enormous periods. Seen this way, the Cassini division becomes a visible record of mathematics expressed through gravity. We cannot watch Mimas pulling individual particles from our vantage point. The force leaves no luminous trail across the rings. Yet when you look through a telescope and notice that dark separation, you are seeing countless small gravitational interactions accumulated into a feature large enough to cross interplanetary space and reach the human eye. Heat can reveal structures that ordinary photographs cannot see. In February 2010, the Cassini spacecraft turned its composite infrared spectrometer toward Mimas and measured thermal radiation escaping from the surface. Researchers expected a familiar pattern, with temperatures largely controlled by sunlight and the changing angle of illumination. The resulting map looked completely wrong. Across part of the Moon appeared a broad region warmer than its surroundings. Its curved boundary resembled the open mouth of the character Pac-Man from the arcade game. Inside that shape, temperatures reached roughly minus 290 degrees Fahrenheit. Nearby terrain could fall below minus 320 degrees Fahrenheit. The strangest detail sat inside Herschel Crater. Instead of behaving like an obvious warm region under sunlight, portions of the crater remained colder than nearby terrain. On the thermal map, Herschel appeared as a cold circular feature positioned inside the warmer pattern, strengthening the accidental resemblance to an enormous eye. Researchers initially searched for an explanation at the surface. The most useful clue came from thermal inertia, a measure of how quickly material changes temperature when heated or cooled. Loose, powdery material responds differently from dense or compacted ice. Two areas receiving comparable sunlight can therefore reach different temperatures because their surfaces store and release heat at different rates. Mimas may contain precisely this contrast. Energetic particles trapped within Saturn's magnetic environment continually strike the moon. Over long periods, that bombardment can alter the physical structure of surface ice. Researchers proposed that some regions become more compact through a process called sintering, where individual ice grains gradually bond together without fully melting. Compacted ice conducts heat differently from loose material. As sunlight moves across Mimas, those differences can produce boundaries visible to infrared instruments, even when ordinary images show little change. The Pac-Man pattern may therefore trace variations in the texture and thermal properties of the uppermost surface. Herschel adds another layer. Material inside the crater may possess different grain sizes, density, or thermal behavior because the impact excavated and rearranged the local terrain. Its temperature signature demonstrates that topography alone cannot explain the map. For scientists, this created an important warning. When we look at an icy moon, brightness and crater patterns reveal only part of its physical state. Infrared measurements can expose differences hidden within material that appears visually similar. Cassini had effectively given us two versions of Mimas. Visible light showed the familiar cratered exterior. Thermal radiation revealed boundaries that did not follow the obvious geography. The Pac-Man pattern did not require active volcanism or exposed liquid water. Surface physics could account for much of it. But its discovery showed how complicated an apparently inactive moon could be, with invisible variations in ice producing an entirely different landscape when viewed through temperature instead of reflected sunlight. Sometimes, the interior of a moon reveals itself through motion. No drilling is required. No exposed material needs to reach the surface. Instead, astronomers can watch how a world rotates and measure departures from the movement expected of a completely solid body. That approach transformed Mimas in 2014. Researchers led by Radwan Tajidine examined images collected by the Cassini spacecraft. They tracked recognizable surface features across photographs taken at different points along Mimas's orbit. From those changing positions, the team reconstructed tiny variations in the moon's orientation. Mimas rocks back and forth. This motion is called physical libration, a small oscillation in the rotation of an orbiting body. Tidally locked moons naturally experience some libration because their orbits are not perfectly circular. Their orbital speed changes slightly, while their rotation remains comparatively steady. From Saturn, Mimas would therefore appear to turn a little from side to side during each orbit. The existence of that motion was expected, its size was not. Cassini measurements indicated a libration roughly twice as large as researchers predicted for a simple, uniformly structured interior. Something about the distribution of mass inside Mimas appeared to amplify its response to Saturn's gravitational pull. Suddenly, the exterior could no longer tell the entire story. Two broad possibilities emerged. Mimas might contain an elongated, rocky core, producing an uneven internal mass distribution beneath its icy exterior. Such a core could alter the moon's rotational response enough to generate the observed wobble. Models showed that this explanation was physically possible, although the required internal geometry would be unusual. The alternative was more radical. A layer of liquid water could separate the outer ice shell from material deeper inside. If the shell were partially decoupled from the interior, Saturn's gravity could make that outer layer rock more freely, increasing the measured libration. You would expect an ocean world to advertise itself. Enceladus displays fractures and active plumes. Europa carries networks of ridges and disrupted terrain. Mimas offered no comparable evidence. Its densely cratered surface appeared ancient, with none of the obvious geological signatures expected from liquid water moving beneath an icy shell. That contradiction made the ocean interpretation difficult to accept. A hidden sea could explain the rotational measurements, yet the surface seemed to argue against it. The study, therefore, did not declare an ocean. Its authors presented internal structures capable of reproducing the observed motion, leaving both an unusual core and a subsurface liquid layer under consideration. Still, the measurement changed the scientific status of Mimas. We could no longer treat its interior as straightforward simply because its exterior appeared inactive. A tiny rotational deviation had exposed uncertainty beneath the ice. For centuries, everything known about Mimas came from light reflected off its surface. Cassini had found information encoded in movement instead. By measuring a rocking motion too small for human eyes to notice directly, scientists discovered that the moon's interior was more complicated than its battered exterior suggested. For most worlds, geological youth is written across the surface. Fresh terrain replaces old craters. Fractures open. Material rises from below. Mimas presents the opposite possibility. An ancient exterior, covering an interior transformation that may have begun surprisingly recently. In February 2024, researchers led by Valerie Laney published a study in the journal Nature. Their analysis used Cassini observations spanning more than a decade, examining subtle changes in Mimas's orbit alongside the rotational behavior already measured from spacecraft images. The results favored a global ocean beneath the ice. According to their models, liquid water may begin roughly 12 to 19 miles below the surface. Above it lies an icy shell, thick enough to isolate the ocean completely from space. Beneath the water sits the moon's rocky interior, providing a boundary where liquid and minerals could interact. Its age made the result even more unusual. The researchers estimated that this ocean may have appeared within roughly the past 25 million years, with some evolutionary models placing major melting within only a few million years. In planetary terms, that is remarkably recent. Earth already possessed complex ecosystems, while the interior of Mimas may still have been largely frozen. The energy required for melting comes from Saturn. Mimas follows a slightly eccentric orbit, meaning its distance from Saturn changes during each revolution. Saturn's enormous gravitational pull, therefore, varies slightly as the moon moves. This changing force deforms the interior, repeatedly flexing material and generating frictional heat. The process is called tidal heating. It allows moons far from strong solar warmth to maintain internal temperatures high enough for liquid water. Given sufficient time and the right orbital conditions, heat can accumulate faster than it escapes through the outer ice. But Mimas created a puzzle. Where were the expected scars? A mature ocean world can reveal internal activity through fractures, resurfaced terrain, or erupting material. Mimas displays none of those obvious signs. The 2024 models offered a different interpretation. If the ocean developed recently, heat from below may simply not have had enough time to transform the outermost shell. Ice conducts heat slowly. Mechanical changes can take even longer. This creates a remarkable geological arrangement. You could stand above a global body of liquid water and see an exterior that still records conditions established long before that water formed. The surface would effectively preserve an older version of the moon. That possibility changes how we identify ocean worlds. We have often searched for surfaces that advertise active interiors. Mimas suggests that some oceans may remain concealed beneath landscapes, offering almost no visible warning. If the interpretation is correct, We are observing an ocean world near the beginning of its internal evolution. Mimas has not reached the outwardly active state seen on Enceladus or Europa. Its transformation remains buried beneath miles of ice, recorded primarily through orbital motion and the gravitational relationship between a small moon and Saturn. A moon can be heated without receiving much warmth from its star. The energy may come instead from movement, gravity, and repeated deformation. Inside icy satellites, this mechanism can preserve liquid water in regions where sunlight alone could never provide enough heat. The source is tidal force. Gravity weakens with distance. When a moon travels close to a massive planet, its near side feels a slightly stronger gravitational attraction than its far side. The difference stretches the moon along the direction toward the planet while compressing it elsewhere. If the orbit were perfectly circular and unchanging, that deformation could remain comparatively steady. Real orbital systems are more complicated. A slightly eccentric orbit carries a moon nearer and farther from its planet during each revolution, changing the strength of the gravitational pull. The interior responds continuously. Rock and ice flex as the tidal stress increases and decreases. Internal friction resists that movement, converting some mechanical energy into heat. You can produce a crude version by repeatedly bending a piece of metal. The material warms because deformation dissipates energy internally. Across astronomical timescales, even modest flexing can matter enormously. Jupiter's moon Io demonstrates the extreme case. Gravitational interactions involving Jupiter, Europa, and Ganymede maintain Io's eccentric orbit. Jupiter then repeatedly deforms the moon, generating enough internal heat to melt rock. The result is the most volcanically active known world in the solar system, covered with lava flows and erupting volcanoes. Around Saturn, Enceladus provides a colder expression of the same physics. Tidal heating helps maintain liquid water beneath its ice. Near the South Pole, fractures provide pathways upward, allowing water vapor and icy particles to erupt hundreds of miles into space. Mimas occupies another regime. Its proximity to Saturn subjects it to substantial tidal forces, yet the amount of heating depends on more than distance. Orbital eccentricity, internal structure, rigidity, and the way energy dissipates inside the moon all influence how much warmth is produced. Once melting begins, the system can change further. Liquid water allows an outer ice shell to move somewhat independently from the deeper interior. That altered mechanical structure affects how tidal energy is dissipated, potentially changing the rate of internal heating. Heat also escapes slowly through thick ice. This creates a competition between energy generated within Mimas and energy conducted outward toward the frigid surface. Where internal production becomes sufficient, ice at depth can reach its melting point while the exterior remains frozen. We therefore do not need sunlight to explain every liquid environment in the solar system. Gravity itself can supply energy, provided the orbital conditions continue feeding deformation into a moon. That principle extends far beyond Saturn. Wherever moons orbit giant planets, tidal forces can create internal heat. A world may receive little stellar warmth and still possess liquid water beneath its surface, powered by the continuing conversion of orbital energy into heat deep inside. For decades, one of astrobiology's most important maps looked like a ring around a star. Worlds inside that ring might be warm enough for surface oceans, move too close, and water could evaporate. Travel too far outward, and exposed water would freeze. Astronomers call this region the habitable zone. More precisely, It describes distances where a rocky planet with suitable atmospheric conditions could maintain liquid water on its surface. Earth occupies that region around the Sunday. Mars lies near its outer reaches, while Venus receives considerably more solar energy closer inward. The concept remains scientifically valuable, but it describes only one arrangement. Mimas lies roughly 887 million miles from the Sunday sunlight. There is dramatically weaker than at Earth. Across its exposed surface, stable liquid water cannot persist under present conditions. Any water reaching the exterior would rapidly freeze or escape depending on its surroundings. Yet water may still remain liquid below. That distinction changes the geography of potentially habitable environments. A world does not necessarily need its star to provide all the energy required for melting. Internal sources can maintain liquid reservoirs beneath insulating layers of ice, separating habitability from surface temperature. We already see this pattern across the outer solar system. Europa circles Jupiter far beyond the traditional habitable zone and possesses strong evidence for a global subsurface ocean. Ganymede also appears to contain extensive liquid water beneath its exterior. Around Saturn, Enceladus maintains an ocean that releases material into space. Titan is believed to contain a deep water ocean beneath its crust while carrying lakes and seas of hydrocarbons on the surface. Mimas now pushes the idea further. Its small size once made a persistent internal ocean seem especially unlikely. If current evidence is correct, even a body this modest can maintain liquid water under suitable gravitational and thermal conditions. That does not make Mimas habitable in any proven biological sense. Liquid water alone cannot establish that an environment supports life. Chemistry, usable energy, long-term stability, and interactions with rocky material also matter. We have no evidence that organisms exist beneath the ice. Still, the search area expands. Consider what happens when we apply this lesson beyond our solar system. Giant planets are common around other stars. Many likely possess moons, although detecting small satellites across interstellar distances remains extremely difficult. Some of those moons could experience gravitational heating while orbiting far beyond their star's traditional habitable zone. A system once dismissed as too cold might therefore contain protected liquid environments underground. The habitable zone was never a universal border separating living possibilities from lifeless space. It is a useful description of where surface water can persist under certain conditions. Mimas reminds us that surfaces are only one place to look. In the universe, warmth can come from stars, radioactive decay, chemistry, and gravity. The possible locations for liquid water extend wherever those energy sources can keep ice from closing completely around it. Place the known ocean worlds beside one another, and no single pattern defines them. Some reveal their water through broken ice, others hide it beneath enormous frozen shells. Together, they show that oceans can survive under conditions unlike anything found on Earth's surface. Europa is among the clearest examples. This moon of Jupiter probably contains a global saltwater ocean beneath roughly 6 to 19 miles of ice. Estimates suggest that its ocean may hold more than twice the liquid water contained in all of Earth's oceans. Its fractured exterior records movement within the icy shell above that hidden sea. Enceladus exposes its interior more directly. Along its south polar terrain, long fractures release jets containing water vapor and icy grains. Cassini repeatedly passed through these plumes, effectively sampling material that originated from the moon's internal ocean without ever landing. Those encounters revealed remarkable chemistry. Instruments detected molecular hydrogen, carbon dioxide, methane, salts, and silica particles. Several findings are consistent with warm water interacting with rock on the seafloor. Such interactions resemble hydrothermal systems on Earth, where heated water circulates through fractured crust and supports rich chemical environments. Titan presents another arrangement. Saturn's largest moon has lakes and seas across its surface, although they contain liquid methane and ethane rather than water. Far below that hydrocarbon landscape, gravitational and rotational measurements support the presence of a global water-rich ocean beneath an icy crust. Around Jupiter, Ganymede appears even more layered. Evidence from magnetic measurements indicates a deep saltwater ocean, potentially arranged between different phases of high pressure ice. Callisto also shows signs of an electrically conductive layer underground, commonly interpreted as a salty ocean beneath its battered exterior. Then we return to Mimas. Among these worlds, its distinction comes from both size and appearance. Mimas is far smaller than Europa, Titan, Ganymede, or Callisto, and smaller even than Enceladus. Yet current evidence suggests that liquid water may persist globally beneath its crust. There are no active plumes available for spacecraft to sample, no widespread networks of young fractures advertise moving ice. The familiar surface gives researchers almost none of the visual clues associated with established ocean worlds. That difference matters scientifically. If a body as small as Mimas can develop and maintain a global ocean, then size alone becomes a weaker filter when we search for hidden water. Other small icy moons previously classified as thoroughly frozen may deserve closer examination. You can imagine the outer solar system differently once that possibility is included. Every cratered satellite is no longer automatically what its surface suggests. Mimas may represent something especially rare, an ocean world whose interior changed recently enough that its exterior has barely responded. Europa and Enceladus show mature interactions between water and ice. Mimas may preserve an earlier stage, allowing us to observe how an apparently frozen moon begins becoming an ocean world from within. Cassini spent years becoming a machine built around patience. Each orbit offered another angle, another measurement, another chance to compare Saturn's moons under changing geometry. For Mimas, those accumulated observations eventually became far more valuable than any single photograph. The mission began on October 15, 1997. Cassini launched from Cape Canaveral, carrying the European Space Agency's Huygens probe, beginning a journey that used gravitational assists from Venus, Earth, and Jupiter. Nearly 7 years later, on July 1, 2004, Cassini entered orbit around Saturn. It stayed for 13 years. During that time, the spacecraft completed 294 orbits of Saturn and performed 162 targeted flybys of its moons. The project united the National Aeronautics and Space Administration, the European Space Agency, and the Italian Space Agency, combining instruments, communications networks, engineering teams, and scientists across several nations. Cassini itself carried 12 scientific instruments. Cameras recorded visible landscapes. Spectrometers separated light into wavelengths that revealed composition and temperature. Radar could investigate surfaces hidden beneath atmospheric haze. Other instruments measured magnetic fields, charged particles, dust, plasma, and the gravitational environment surrounding Saturn. For Mimas, February 13, 2010 provided one of the mission's closest views. Cassini passed about 5,900 miles from the moon, photographing cratered terrain at high resolution while its infrared instruments examined surface temperatures. Those observations produced the unusual thermal pattern that distinguished regions invisible in ordinary photographs. Yet, some of Cassini's most important measurements required no camera. As the spacecraft traveled through Saturn's system, scientists transmitted radio signals between Cassini and Earth. Gravity from nearby bodies altered the spacecraft's motion by extremely small amounts. Those changes appeared as measurable shifts in the frequency of the returning radio signal. This technique allowed researchers to investigate mass, orbital motion, and internal structure with extraordinary precision. Combined with repeated imaging, Cassini's long observational record provided the information needed to track Mimas across many years. We can now extract clues from tiny changes that would have been impossible to recognize during a brief encounter. The mission ended deliberately on September 15, 2017. Cassini was running low on propellant, leaving engineers unable to guarantee control forever. An uncontrolled spacecraft might eventually collide with Enceladus or Titan, potentially carrying terrestrial microbes into environments important to astrobiology. Controllers therefore directed Cassini into Saturn. Its instruments continued transmitting during the descent, sampling the planet's upper atmosphere until communication was lost. By then, the mission had returned hundreds of gigabytes of scientific data and more than 450,000 images. Cassini no longer exists as a spacecraft, but its measurements remain active scientific material. Researchers continue revisiting archived observations with improved models and new questions. Mimas demonstrates why that matters. Data gathered during an expedition completed years ago can still reveal properties its original investigators had not yet imagined. Before spacecraft could cross the solar system, discovery depended on glass, polished metal, darkness, and the patience of a human observer. William Herschel worked in that earlier age, when a distant moon could announce itself only as a moving point among thousands of stars. Herschel was born in Hanover in 1738. Astronomy was not his original profession. He trained as a musician, moved to England, and earned his living teaching and performing music. His interest in mathematics and optics gradually pulled him toward the night sky. He began building telescopes himself. Herschel became exceptionally skilled at grinding and polishing speculum metal mirrors, allowing him to construct increasingly powerful reflecting telescopes. In 1781, using one of his instruments, he discovered Uranus. It became the first planet identified in recorded history beyond those visible to unaided human eyesight. That achievement brought royal support and greater resources. By 1789, Herschel had completed his enormous 40-foot telescope at Slough, England. The instrument took its name from its approximate length. Its primary mirror measured almost 4 feet across, making it the largest telescope of its era. Operating it was difficult. Assistants helped position the massive structure while Herschel observed near the upper end of the tube. The instrument collected enough light to reveal objects that smaller telescopes struggled to separate from Saturn's glare. On August 28, 1789, Herschel discovered Enceladus. Then, on September 17th, he identified another satellite. That second moon was Mimas. Through Herschel's telescope, there was no visible cratered landscape. No observer could distinguish mountains, impact basins, or surface ice. Mimas appeared as a tiny point whose changing position betrayed its orbit around Saturn. From such limited information, Herschel established the existence of an entire world. He never gave it the name we use today. Decades later, his son John Herschel proposed names for several Saturnian moons, drawing from the giants of Greek mythology. Mimas and Enceladus entered astronomical language through that later convention. William Herschel's work extended far beyond Saturn. With his sister, Caroline Herschel, an accomplished astronomer in her own right, he conducted extensive surveys of the heavens. He catalogued thousands of nebulae and star clusters and attempted to infer the structure of the Milky Way from star counts. In 1800, another experiment produced an unexpected discovery. Herschel placed thermometers beyond the red portion of a spectrum created by sunlight passing through a prism. The temperature increased where no visible light appeared. He had detected infrared radiation. Herschel died in 1822 at 83 years old. He never saw Mimas as a world. Today, his surname crosses its surface. Herschel Crater preserves the discoverer's name on the moon itself. When you see that immense circular feature in spacecraft photographs, we are connecting two technologies separated by centuries: a handmade telescope that found a point of light, and machines that eventually revealed the landscape hidden inside it. To understand Mimas as a world, we have to place Saturn at the center of its story. The moon's orbit, internal stresses, and long-term evolution are inseparable from the giant planet governing its motion. Saturn is the sixth planet from the Sun, traveling at an average distance of roughly 888 million miles. It is enormous. About 95 Earth masses are contained within the planet, making Saturn the second most massive world orbiting the Sunday. Yet its average density is remarkably low. Saturn is less dense than water, a property often illustrated with an impossible experiment. Given an ocean large enough, the planet would float. In reality, no container could hold such a world, but the comparison captures how much of Saturn consists of hydrogen and helium rather than dense rock. Around that immense globe spreads its famous ring system. The main rings extend across hundreds of thousands of miles, while remaining astonishingly thin compared with their width. In many regions, their vertical thickness is measured in only tens of feet. Countless particles of water ice circle Saturn there, ranging from tiny grains to chunks as large as buildings. Above the rings, Saturn's atmosphere moves with extraordinary speed. Equatorial winds can reach more than 1,000 miles per hour. Only Neptune is known for faster planetary winds. Vast bands of clouds stream around Saturn, driven by heat rising from deep inside the planet and by its rapid rotation. At the North Pole, atmospheric motion takes an even stranger form. A persistent six-sided jet stream surrounds the pole, producing Saturn's famous hexagon. Each side spans thousands of miles. Spacecraft observations have followed this structure for decades as winds race around its perimeter. Saturn's magnetic environment is equally unusual. Its magnetic field is aligned extraordinarily closely with the planet's rotation axis. Planetary magnetic fields are normally tilted to some degree, making Saturn's near alignment difficult to reconcile with standard models of how such fields are generated deep inside giant planets. For Mimas, however, gravity is Saturn's most consequential influence. Every orbit takes the Moon through the gravitational geometry of this enormous system. Saturn keeps Mimas bound, controls its orbital motion, and provides the tidal forces capable of deforming its interior. Those forces are small from one moment to another. Across geological time, their accumulated effects become profound. If Mimas truly contains liquid water beneath its ice, Saturn supplies the gravitational energy that helps make such an interior possible. So when you picture Mimas circling beside the rings, you are seeing a moon whose present condition cannot be separated from its parent planet. Its orbit, internal flexing, resonances, and thermal evolution all unfold inside Saturn's gravitational domain. We can study Mimas as an individual world, but the forces shaping it belong to a much larger system. A cratered surface can function like an ancient archive. On Mimas, each overlapping scar preserves part of a history that Earth has largely erased. Reading that archive carries us toward the formative ages of the Saturn system. The broad story begins around 4.5 billion years ago, when the planets and moons were assembling from material surrounding the young Sunday. Saturn gathered enormous quantities of gas, while a disk of ice, dust, and rocky material developed around the growing planet. Within that circumplanetary disk, solid particles collided and accumulated. Gravity gradually assembled larger bodies. Eventually, moons emerged. Exactly when Mimas acquired its present form remains uncertain. Traditional models place the formation of Saturn's major moons near the beginning of the solar system. Yet some models suggest that smaller inner moons could have been destroyed and rebuilt from ring material much later. Under those scenarios, something resembling modern Mimas might be only around 100 million years old. On Earth, that places its possible reconstruction within the Cretaceous period, when dinosaurs still occupied ecosystems across the planet. Such a young age remains debated, and researchers continue testing competing models of Saturn's rings and moons. Either history unfolded within a violent planetary system. Between roughly 4.1 and 3.8 billion years ago, many worlds experienced intense bombardment. This proposed interval is commonly called the Late Heavy Bombardment, although its exact timing and intensity remain subjects of scientific debate. Early models connected that bombardment with migrations of the giant planets. Jupiter, Saturn, Uranus, and Neptune may have shifted substantially from their original orbits. Their changing gravitational relationships scattered smaller bodies across the solar system, redirecting asteroids and icy objects onto new trajectories. For a small moon, those encounters could be devastating. Mimas carries abundant evidence of impacts across its exterior. The largest collision preserved there produced Herschel Crater, though scientists cannot assign that event a precise date. Its impactor may have been an asteroid or cometary body moving through the Saturn system during an earlier era of greater debris. Whatever its origin, the collision became part of a much larger record. Look across Mimas, and you find crater upon crater, some fresh in outline, others softened beneath later impacts. Their arrangement records relative age. A crater lying across another must have formed later, allowing scientists to reconstruct sequences without knowing every absolute date. Earth offers almost nothing comparable. Wind, flowing water, volcanism, glaciers, and plate tectonics continually alter our planet's exterior. Ancient impact scars disappear beneath sediments or are recycled into the mantle. Mimas lacks those powerful resurfacing processes. With almost no atmosphere or weather, its icy crust retains events that would vanish rapidly on Earth. Even if portions of that crust formed later than once assumed, the landscape remains an unusually persistent record. So when we examine Mimas, we are reading accumulated collisions rather than a single catastrophe. Its battered exterior preserves the consequences of orbital instability, wandering debris, and repeated impacts within Saturn's evolving neighborhood. The Moon carries that history across its surface, written crater over crater in ancient ice. A landscape can reveal its age through what has failed to disappear. Across Mimas, impact scars remain layered over older scars, preserving generations of collisions in a crust that has undergone remarkably little resurfacing. From orbit, the Moon resembles a frozen record left largely intact. Beyond Herschel, craters dominate almost every region Cassini photographed. Their abundance tells planetary scientists that much of the visible terrain is ancient. On geologically active worlds, volcanism, erosion, tectonic motion, or fresh deposits gradually erase impact structures. Mimas offers little evidence that such renewal has operated extensively across its exterior. Cassini resolved craters spanning an enormous range of sizes. Some extend for many miles, while smaller features measure only hundreds or thousands of feet across. Overlapping rims provide a chronology. When one crater cuts through another, you can identify which collision happened later, building a relative history directly from the terrain. Many features also carry names drawn from Arthurian legend. Bran, Morgan, and Merlin are among the prominent named craters, following conventions approved by the International Astronomical Union. Their names give familiar labels to landscapes formed by impacts unimaginably distant from the stories that inspired them. Between those craters, another detail becomes important. Mimas possesses very few broad, smooth plains, resembling terrain found on more geologically active icy moons. Such plains can form when warmer material resurfaces older landscapes, covering previous craters and producing younger ground. Here, that signature is largely absent. This makes the probable ocean beneath Mimas especially unusual. Its exterior presents the appearance of a deeply inactive body, while evidence from its motion suggests liquid water may exist miles below. The crust has apparently preserved its ancient texture, even as conditions deeper inside changed. Water ice dominates that crust. Spectral observations from Cassini also revealed variations in surface composition and physical texture, allowing researchers to distinguish regions with different thermal properties. What appears visually uniform can therefore behave differently when sunlight arrives and heat escapes. Gravity would make the landscape stranger still. Surface acceleration on Mimas is only about 2/10 of a foot per second squared, less than 1% of Earth's gravity. If you weigh 150 pounds on Earth, the same person would exert a weight of roughly 1 pound on Mimas. Movement there would be transformed. A modest jump could carry you far higher and keep you airborne, much longer than anything familiar on Earth. Loose material disturbed beneath your boots would fall back slowly under the moon's weak pull. Its small size would also reshape your view. Mimas spans only about 246 miles, so its horizon would sit unusually close compared with Earth's. From suitable terrain, the curvature beneath you would become easier to recognize across the surrounding landscape. That nearby horizon would frame terrain almost entirely carved by impacts. Crater walls, broken rims, slopes, and overlapping basins preserve a surface with few signs of large-scale renewal. Beneath that battered ice, however, the moon's interior appears to have followed a very different geological history. Absence can become evidence when every expected feature is missing. If liquid water truly surrounds the interior of Mimas, its surface seems remarkably disconnected from what lies beneath. There are no towering plumes, broad fractures, or obvious regions where internal activity has broken through the crust. Nearby Enceladus presents the opposite picture. Its subsurface ocean communicates directly with space through fractures near the South Pole. Water vapor, ice grains, salts, and other materials erupt through these openings, forming plumes that extend hundreds of miles above the moon. Cassini repeatedly observed and sampled this material. Europa carries another visible signature. Its icy exterior is crossed by long ridges, fractures, disrupted blocks, and regions known as chaos terrain. These landscapes record movement within an ice shell influenced by warmer material and an ocean below. Mimas offers almost none of those clues. Its cratered exterior retains an ancient appearance, largely undisturbed by widespread recent resurfacing. That created a serious problem for the ocean interpretation. How could a global body of liquid water exist beneath such an apparently inactive crust without leaving recognizable geological traces? The proposed answer depends on time. Research published in Nature in 2024 indicated that the ocean may have formed only within roughly the past 5 to 15 million years. For planetary geology, that is remarkably recent. The liquid layer could therefore be younger than many structures preserved above it. Models place the ocean beneath an ice shell roughly 12 to 19 miles thick. Heat rising from deeper layers gradually changes the shell from below. Yet thick ice does not instantly fracture simply because liquid water develops underneath. Its mechanical response unfolds across geological timescales. Imagine the boundary moving upward through the crust as deeper ice melts. The solid shell slowly becomes thinner. Internal stresses change with its thickness, temperature, and orbital flexing. Eventually, fractures may become easier to create and propagate toward the surface. That stage may not have arrived. If the young ocean model is correct, we are seeing Mimas during an unusual interval when its interior has transformed faster than its exterior. The surface still preserves terrain inherited from an earlier thermal state. Several miles beneath it, conditions may already belong to an ocean world. Over tens of millions of years, continued heating could thin the shell further. Greater deformation might eventually produce fractures or other signs of activity. Whether Mimas will actually develop Enceladus-like geysers remains uncertain because its orbital evolution and internal heat supply can change. That uncertainty matters. A hidden ocean does not require a spectacular surface display. Worlds capable of maintaining internal liquid water may exist without plumes announcing their presence to passing spacecraft. Mimas therefore changes what you might search for when examining an icy moon. A heavily cratered exterior can conceal a much younger interior. Geological activity may begin far below the surface, leaving the crust apparently unchanged while an ocean develops underneath. If that interpretation survives future testing, Mimas represents something rarely accessible in planetary science, an ocean world observed near the beginning of its internal transformation. Before its exterior has fully responded, life requires more than water. That distinction matters whenever we consider Mimas. A buried ocean would make this small Saturnian moon more interesting to astrobiology. Yet liquid water alone tells us nothing certain about biology. It gives chemistry somewhere to operate. For life as we understand it, researchers generally look for three broad ingredients. There must be liquid water, usable energy, and suitable chemical building blocks. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are especially important because terrestrial organisms depend heavily upon them. Mimas may already satisfy two requirements. Its proposed ocean provides persistent liquid water beneath the ice. Tidal heating supplies an internal energy source independent of sunlight. More intriguing possibilities appear near the rocky seafloor, assuming the ocean reaches or interacts with rock below. Water circulating through warm rock can drive chemical reactions. On Earth, similar interactions around hydrothermal systems create steep chemical gradients, meaning neighboring environments contain different concentrations of reactive substances. Microorganisms can exploit those differences as energy sources. Whether comparable chemistry exists inside Mimas remains unknown. Cassini detected no direct evidence of complex organic molecules originating from this moon. That contrasts sharply with Enceladus. Material erupting from Enceladus allowed Cassini to detect salts, molecular hydrogen, carbon dioxide, methane, and complex organic compounds associated with its internal ocean. Those measurements make Enceladus unusually accessible. A spacecraft can sample material from deep inside the moon simply by passing through its plumes. The ocean effectively delivers samples into space. Mimas offers no such convenience. Its suspected water reservoir lies beneath roughly 12 to 19 miles of ice. Reaching it directly would therefore require technologies far beyond anything currently deployed on another world. Even confirming its composition remotely presents substantial challenges. So, why does Mimas matter so much? Its importance comes from probability. If a body only about 250 miles across can maintain an internal ocean, then planetary scientists may have underestimated how easily liquid reservoirs develop inside icy moons. Size and surface appearance become less reliable filters. You could look across another planetary system and see frozen satellites circling a distant giant planet. Some might appear inert. Their surfaces could preserve ancient craters without obvious fractures or eruptions. Yet, gravitational flexing might still maintain water beneath miles of ice. The scale grows rapidly from there. Our Milky Way contains at least 100 billion stars, with planets appearing to be common around them. Many planetary systems likely include giant worlds, and giant worlds can possess families of moons. Even if only a modest fraction develop internal oceans, the potential number of hidden aquatic environments becomes enormous. None of this demonstrates that life begins easily. We still do not know how frequently chemistry crosses the threshold into biology, even when favorable ingredients coexist. Mimas changes a different part of the equation. It suggests that places capable of hosting those ingredients may be more abundant than their surfaces reveal. A world can appear frozen, ancient, and inactive while maintaining an unseen environment where water, rock, heat, and chemistry meet beneath the ice. Saturn has gone unvisited since Cassini entered the planet's atmosphere in September 2017. Its moons continue circling beyond direct human observation, while the measurements already returned from that system keep producing new interpretations. Mimas now gives scientists another reason to consider going back. One spacecraft is already being built for that distant neighborhood. The National Aeronautics and Space Administration's Dragonfly mission is scheduled to launch in 2028 and reach Titan in late 2034. Its destination is Saturn's largest moon, where a car-sized rotorcraft will fly between different locations during a planned multi-year investigation. Dragonfly will never approach Mimas, yet its work can still matter there. Titan contains abundant organic chemistry, and Dragonfly will examine how complex carbon-bearing compounds behave across an icy world. Those measurements should improve our understanding of chemistry throughout the Saturn system. Elsewhere, another generation of ocean world exploration is already underway. The European Space Agency launched the Jupiter Icy Moons Explorer on April 14, 2023. After a long sequence of planetary gravity assists, the spacecraft is expected to reach Jupiter in July 2031. There it will investigate Europa, Callisto, and especially Ganymede, three worlds associated with buried water reservoirs. Its instruments were designed to examine ice, geology, gravity, magnetic environments, and possible habitats. Techniques refined around Jupiter could help shape the scientific architecture of future missions to Saturn's icy moons. For Mimas, precision would be essential. A dedicated spacecraft could repeatedly measure its physical libration, the small rotational rocking that first exposed its unusual interior. Multiple close encounters at different positions in Mimas's orbit would allow scientists to separate competing internal models with far greater accuracy than Cassini achieved. Ice penetrating radar could provide another route. Radar pulses transmitted toward the surface can reveal boundaries beneath ice by recording how radio energy reflects from different layers. Similar principles are used to investigate buried structures beneath terrestrial ice sheets. Such measurements could constrain the thickness and structure of Mimas's outer shell. Combined with gravity observations and rotational data, they might determine whether liquid water truly surrounds the moon's deeper interior. Getting those instruments there remains difficult. Depending on where the planets occupy their orbits, Earth and Saturn can be separated by roughly 750 million to more than 1 billion miles. Spacecraft therefore require years of travel, carefully planned trajectories, reliable power, and communications capable of crossing enormous distances. No dedicated Mimas mission is currently approved. Concepts for returning orbiters to the Saturn system have been studied, but a future project would still require scientific prioritization, funding, development, and years of engineering. Cassini transformed Mimas without being designed around its hidden ocean. A spacecraft built with that possibility in mind could examine the moon differently, treating its tiny rotational motions, buried ice structure, and gravitational field as direct evidence of an interior that remains beyond our sight. A ring gap can be traced back to arithmetic. Around Saturn, countless particles follow individual paths, yet their collective structure responds to repeated gravitational timing. Mimas participates in that architecture through orbital resonance, where recurring gravitational pulls accumulate instead of averaging away. Near the Cassini division, the pattern is especially clear. Particles near its inner edge encounter a 2-to-1 resonance with Mimas. They complete roughly 2 circuits around Saturn during each orbit of the moon. Mimas therefore tugs them at repeating orbital positions. Over time, those small disturbances alter particle orbits and help maintain a major boundary within the rings. The same principle appears far beyond Saturn. Pluto and Neptune occupy a 3-to-2 orbital resonance. Neptune completes 3 journeys around the Sun, while Pluto completes 2. Their paths even cross in distance from the Sun, yet the resonance controls their relative positions so effectively that close encounters are avoided. This arrangement has remained stable across immense spans of time. Around Jupiter, resonance becomes even more intricate. Io, Europa, and Ganymede participate in the Laplace resonance. For every orbit completed by Ganymede, Europa completes about 2, and Io about 4. Their gravitational interactions continually influence orbital eccentricity, meaning how far each orbit departs from a perfect circle. That matters inside the moons themselves. Repeated orbital distortions help maintain tidal flexing within Io and Europa. On Io, the resulting heat contributes to extraordinary volcanic activity. Europa receives enough internal energy to help sustain conditions associated with its buried ocean. Orbital mathematics can therefore influence geology hundreds of miles beneath a moon's path. We find comparable structures among smaller bodies. The asteroid belt contains regions depleted of objects called Kirkwood gaps. These correspond to orbital resonances with Jupiter. An asteroid repeatedly receiving gravitational nudges at particular intervals can gradually acquire a more eccentric orbit, clearing it from that region. Resonance does not always create stability. Depending on the configuration, it can preserve an orbit, excite its eccentricity, move material, or remove objects from particular zones. What matters is repetition. Gravity applied with consistent timing can transform tiny effects into planetary architecture. Mimas embodies both sides of this process. Its cratered surface preserves evidence of collisions, while its present orbit imposes regularity upon surrounding ring particles. Ancient impacts altered the moon. Repeating gravity allows the moon to alter its environment in return. Similar relationships have been discovered around other stars. Some exoplanet systems contain planets whose orbital periods lie near resonant ratios, offering clues about migration and long-term evolution. Resonance can reveal how planets moved after formation and how their gravitational relationships changed. So when you look at Mimas beside Saturn, its importance extends beyond one small moon. The same gravitational rules shaping those rings also operate among asteroids, planets, moons, and distant planetary systems. Across radically different scales, repeated motion leaves patterns that mathematics can recognize. Water behaves differently from most familiar substances before an ocean world even forms. As it freezes, its molecules arrange themselves into an open crystal structure. The solid, therefore, occupies more space and becomes less dense than the liquid beneath it. That simple molecular arrangement helps shape entire moons. Newly frozen water tends to remain above liquid water, allowing an outer shell to grow from the top downward. That shell also slows the escape of internal heat. For Mimas, this matters enormously. A buried ocean can remain liquid beneath miles of frozen material, even while the exposed surface experiences extreme cold. Heat generated within the moon must travel through that shell before escaping into space. Ice becomes both crust and thermal barrier. Yet the ice deep inside a moon does not necessarily resemble the ice in your freezer. Pressure changes its crystal arrangement. Scientists call these arrangements ice phases, distinct structural forms of solid water created under different combinations of pressure and temperature. Several high-pressure phases are denser than liquid water. In sufficiently large ocean worlds, such exotic ice can form beneath an internal ocean. The liquid may then become trapped between ordinary ice above and dense ice below, separating water from the rocky interior. Mimas appears small enough to avoid that particular arrangement. Current interior models allow its suspected ocean to contact rock directly. That boundary matters because warm water interacting with minerals can release dissolved compounds and create chemical gradients. Similar water and rock reactions occur around hydrothermal systems on Earth. Such environments have become central to research on life's origins. Some hypotheses place important stages of early terrestrial chemistry near hydrothermal vents, where mineral surfaces, heat, water, and reactive compounds coexist. We cannot assume the same processes occur on Mimas, but direct contact between ocean and rock makes them physically possible. Water also dissolves an extraordinary range of substances, allowing molecules and ions to circulate and react. An internal ocean can therefore become a complex chemical environment. Even Mimas's battered surface has been shaped by these properties. During the Herschel impact, enormous amounts of kinetic energy entered an ice-rich crust. Some material near the collision site may have melted temporarily before losing heat and freezing again. Any resulting liquid would have been brief and localized, transformed by impact energy, rather than long-term internal warmth. Ice can preserve ancient scars, conduct heat, insulate buried water, and change structure under pressure. The same substance can behave as rigid terrain near the surface and flow slowly deeper below. So when we picture Mimas, water occupies almost every layer of its history. Frozen water records impacts above. Solid ice controls heat moving outward. Beneath it, liquid water may interact with ancient rock. One molecule, arranged in different ways, helps determine whether this small moon remains frozen throughout or carries an ocean inside. A grain of ice can travel between worlds in the Saturn system. Released from one moon, it may enter orbit, encounter charged particles, cross another moon's path, and eventually settle onto a surface far from where it began. Seen this way, Saturn is more than a planet surrounded by separate objects. Its neighborhood continually exchanges matter and energy. Enceladus provides one of the clearest examples. Material escaping from its south polar plumes spreads along its orbit, supplying much of Saturn's diffuse E-ring. Those particles are predominantly water ice, accompanied by compounds carried upward from the moon's interior. Some eventually reach neighboring moons. Mimas moves through this shared environment inside the E-ring. Fresh particles originating from Enceladus can strike its ancient surface, depositing an extremely thin coating of material transported across the Saturn system. The exchange is gradual, yet geological time allows countless encounters to accumulate. Mimas also influences its surroundings gravitationally. Its orbital resonances help organize portions of Saturn's rings, changing where particles can maintain stable paths. Other moons produce their own resonances, waves, gaps, and disturbances. The rings respond continuously to these gravitational relationships. Matter travels through another pathway as well. Titan possesses a dense atmosphere dominated by nitrogen, where sunlight and energetic particles drive complex organic chemistry. Some atmospheric particles escape Titan and enter Saturn's broader magnetospheric environment, although their distribution through the system is complex. Saturn's magnetosphere adds another layer. A magnetosphere is the region where a planet's magnetic field strongly controls charged particles. Saturn's extends far beyond Mimas and commonly reaches beyond Titan, although its boundary changes as conditions in the solar wind vary. Mimas spends every orbit immersed within that electromagnetic domain. Energetic electrons and ions strike its exposed ice. Over long periods, this irradiation can break molecular bonds, create new chemical products, and alter surface properties. Meanwhile, incoming material can cover or modify some of those processed regions. The surface we observe is therefore shaped by both local history and particles arriving from elsewhere. Even the direction of bombardment matters, because Mimas keeps one hemisphere generally facing forward along its orbit. Different regions encounter the surrounding particle environment differently. This can contribute to variations in surface appearance and composition. When we place these processes together, the boundaries between individual worlds become less absolute. Enceladus contributes material to space. Saturn controls charged particles and tidal forces. Ring particles respond to moons, while moons move through material associated with the rings. Mimas participates at several levels simultaneously. It receives foreign ice, reshapes nearby orbital structure, experiences radiation from Saturn's magnetic environment, and responds internally to Saturn's gravity. From a distance, you see one cratered moon beside an enormous planet. At closer scales, every orbit places Mimas inside overlapping streams of matter, gravity, radiation, and ice. The moon belongs to a system whose parts continually leave traces upon one another. There is a boundary beyond which even excellent data cannot carry us. For Mimas, that boundary lies beneath its cratered ice, where no instrument has directly observed liquid water. Cassini transformed our understanding of the moon, yet the central claim remains technically unconfirmed. An ocean is presently the strongest interpretation of several measurements, rather than an object we have directly detected. The evidence became especially compelling in 2024. Researchers writing in Nature combined orbital motion with rotational behavior and thermal evolution models. Their results favored a global ocean beneath the crust. Still, scientific confirmation demands more than one persuasive model. Independent measurements, ideally gathered by another spacecraft with different instruments, would provide a stronger test. Much depends on libration, the small periodic wobble in Mimas's rotation. Cassini measured the moon while racing through the Saturn system, and researchers reconstructed subtle motions from imaging and radio tracking. Those measurements reached remarkable precision, yet every observation contains uncertainty. Small systematic effects in spacecraft position, camera geometry, gravitational modeling, or data processing can influence the internal structure inferred from them. Other possibilities, therefore, remain open. An unusually shaped rocky core could alter the rotation. An asymmetric distribution of mass inside Mimas might produce part of the observed wobble without requiring a global ocean. These alternatives have become less favored as models improve, but they have not vanished completely. The surface adds another ambiguity. Its ancient terrain can fit a recently formed ocean whose warmth has not yet extensively reshaped the exterior. But an undisturbed surface alone cannot demonstrate liquid below. You can read the crust for clues, yet it does not provide a direct view into the interior. This is where scientific uncertainty becomes useful. A hypothesis makes predictions, observations test them, and new evidence changes the confidence assigned to each explanation. The ocean model currently survives that process well. It explains several otherwise puzzling properties of Mimas within one physical framework. Probability, however, is different from certainty. A dedicated spacecraft could narrow that distinction dramatically. Repeated close flybys could map tiny variations in gravity across the moon. More precise rotational measurements could refine the libration signal. Ice-penetrating radar might search for reflections from a boundary between solid ice and liquid water. Together, these methods could determine the thickness and structure of the outer shell. Until such measurements exist, we have to preserve the distinction the evidence requires. Mimas may contain a young global ocean, and current research gives that possibility substantial scientific support. We cannot yet say that a spacecraft has found the water itself. That limitation is part of how knowledge advances. Science allows strong conclusions while keeping their uncertainty visible. On Mimas, the evidence has brought us remarkably close to an unseen ocean, but the final confirmation still belongs to observation. Long before anyone knew its surface, Mimas already carried a story. The name came from ancient Greece, where Mimas belonged to the giants, beings born from Gaia, the personification of Earth. They challenged the Olympian gods during the Gigantomachy, a vast mythical struggle over divine order. Ancient storytellers placed conflict on a cosmic scale centuries before telescopes existed. Accounts differ about Mimas's fate. Some traditions associate his defeat with Hephaestus, god of fire and metalworking. Others connect him with Ares and the violence of battle. These variations were normal within Greek mythology, whose stories changed across poets, regions, and generations. The Gigantomachy itself became more than a tale of combat. Greek artists and writers used it to represent order, overcoming destructive forces, and civilization overcoming disorder. When astronomers later gave that ancient name to Saturn's moon, they could not know how strangely appropriate it might become. The physical Mimas carries the mark of an enormous collision. Herschel Crater dominates its appearance, evidence of an impact severe enough to have approached the limits of the moon's survival. Yet the body endured. Beneath that battered exterior, modern measurements now suggest another unexpected persistence. Liquid water maintained deep within the ice. Its geography carries another human story. Herschel Crater commemorates William Herschel, who discovered Mimas in 1789. Here, mythology meets scientific history. A giant from an ancient cosmology shares one world with the name of an astronomer who expanded the known solar system using instruments built by human hands. Then popular culture added another layer. When detailed images revealed the enormous circular crater, viewers noticed its resemblance to the Death Star from Star Wars. The comparison was irresistible. Yet the fictional space station appeared on cinema screens before spacecraft had shown Mimas clearly enough for that resemblance to become widely recognized. So you can trace several eras of human imagination across one small moon. An ancient giant provides the world's name. An 18th century astronomer gives his name to its defining scar. A 20th century fictional weapon supplies its familiar visual comparison. 21st century planetary science then introduces something none of those stories anticipated: evidence for an ocean hidden below. Scientific naming serves practical purposes, allowing researchers to identify places consistently across maps, papers, and missions. The International Astronomical Union oversees those conventions today. But names also preserve cultural memory. They make distant landscapes easier for us to discuss without changing the physical worlds themselves. Mimas would orbit Saturn regardless of what we called it. Herschel Crater would remain exactly where the impact left it. The possible ocean would continue beneath the ice without knowing either name. The stories belong to us. Across mythology, astronomy, cinema, and planetary science, humans repeatedly encounter unfamiliar worlds and give them recognizable language. We place distant objects inside narratives because names turn coordinates into places, and places become part of how we understand the universe. Numbers behave differently in deep space. On Earth, distance is something we cross in hours. Around Saturn, distance becomes part of the physics itself. Mimas travels with its planet roughly 889 million miles from the Sunday sunlight. Crossing that enormous separation requires about 79 minutes. Every illuminated crater, therefore, reflects light that has already spent more than an hour traveling outward. When you observe Saturn from Earth, you never see its system as it presently exists. The light entering your telescope carries an earlier version of Mimas. Even before that light reaches us, the moon has continued moving along its orbit. Astronomy always contains this delay. Distance becomes time. Human spacecraft make the scale more tangible. Voyager 1 photographed Mimas during its Saturn encounter in 1980, revealing details impossible to resolve from Earth. Decades later, Voyager 1 has traveled more than 15 billion miles from our planet. A radio transmission, moving at light speed, requires more than 22 hours to cross the distance between the spacecraft and Earth. Cassini followed a very different route. Its voyage from Earth to Saturn lasted 6 years and 261 days. The spacecraft traveled roughly 2,200,000,000 miles along a looping interplanetary trajectory. Gravity assists from Venus, Earth, and Jupiter changed its velocity without requiring impossible quantities of onboard fuel. Reaching Saturn meant using the motion of planets themselves. Then there is Mimas. The moon measures only about 246 miles across. Herschel Crater occupies an astonishing fraction of that diameter, spanning roughly 86 miles from rim to rim. Place that distance on Earth, and it could stretch across entire metropolitan regions. Yet here it forms one impact scar on a world small enough for its curvature to become apparent across the landscape. Near Herschel's center rises a peak roughly 4 miles high. That mountain was produced during the impact as compressed material rebounded upward, leaving a structure comparable in height to some of Earth's great peaks. Its scale records the energy released when the crater formed. Below this landscape, the proposed ocean introduces numbers we cannot yet measure directly. Its thickness, volume, salinity, and exact boundaries remain uncertain. Even so, a global layer of liquid inside a moon 246 miles wide could represent an immense reservoir hidden beneath comparatively little visible terrain. You can hear these figures and understand each one individually. 889 million miles, 79 minutes for sunlight, more than 22 hours for a distant spacecraft signal, an 86-mile crater on a 246-mile moon. Together, they describe something more useful than an impression of vastness. They establish the physical dimensions within which Mimas actually exists. Space does not require exaggeration. Its distances, travel times, mountains, impacts, and hidden depths already exceed the scales our everyday experience prepared us to imagine. For almost all of its history, Mimas existed beyond the reach of any known observer. Saturn held it in orbit, impacts altered its surface, and gravity worked through its interior. None of these processes required recognition. The moon simply continued around its planet, while ages passed elsewhere in the solar system. At some unknown time, the object that formed Herschel Crater arrived. It struck with enough energy to reshape a substantial portion of Mimas, material excavated outward. Shock waves traveled through the small body, and the crater floor rebounded upward into its central peak. No human watched the collision. If no other technological intelligence witnessed it, the event entered history without an audience. That distinction matters when we consider deep time. Events can be enormous without ever becoming experiences. Mountains rise, worlds collide, oceans form, and orbits evolve, whether anyone records them or gives them names. The proposed ocean deepens that perspective. Current models suggest liquid water may have developed beneath Mimas between 5 million and 15 million years ago. If so, its formation began long before humans possessed telescopes. Water accumulated beneath ice while pressure, heat, minerals, and gravity followed physical laws continuously. For millions of years, an entire hidden environment may have existed beyond every human sense. Then, on September 17th, 1789, something changed from our perspective. William Herschel observed a faint point near Saturn and recognized its motion against the background stars. Mimas entered human knowledge. Even then, nobody knew its appearance. Nearly 2 centuries passed before Voyager. One approached Saturn in 1980. Its cameras transformed that distant point into a world with visible terrain. Images transmitted across interplanetary space reached Earth and were reconstructed on screens at the Jet Propulsion Laboratory in Pasadena. For the first time, human beings could examine the shape and scars of a moon that had existed for an immense span before our species understood it was there. Depending on which formation models eventually prove correct, Mimas may have spent hundreds of millions or more than 4 billion years beyond human awareness. Our entire recorded history occupies only a tiny interval beside such durations. And Mimas is hardly exceptional. Most objects in the universe have never been directly observed. Countless planets orbit stars too faint or distant for present instruments. Smaller moons may circle those planets unseen. Asteroids cross remote systems. Oceans may move beneath alien ice, while chemistry proceeds without ever reaching a telescope. The universe is about 13.8 billion years old. Human astronomy occupies only the smallest fraction of that history. Observation reveals what was already happening. That is the peculiar remoteness Mimas represents. Its existence did not begin when Herschel detected it, nor when Voyager 1 photographed it, nor when Cassini measured its motion. Those moments changed us and our knowledge. Mimas had already been there, circling Saturn through ages that passed without our awareness. Survival can look purposeful when we encounter only what remains. Mimas offers a useful correction to that instinct. The impact that excavated Herschel Crater released an extraordinary amount of energy, comparable to billions of nuclear weapons by some estimates. Yet the moon remained gravitationally bound, damaged almost beyond recognition, but still a moon. Nothing in that outcome involved intention. Mimas possessed no capacity to resist its destruction. Its survival followed from physics, the strength and behavior of ice, its internal structure, the impactor's mass, and the exact geometry and speed of the collision. Those variables happen to produce devastation without complete disruption. Change them slightly, and Saturn might have another story. A larger projectile could have dispersed Mimas into fragments. Greater speed would have increased the impact energy sharply. A different trajectory could have transmitted stress through the body in another way. The present moon and the gravitational influence it exerts on Saturn's rings would never have existed in its familiar form. William Herschel would have found no Mimas on September 17, 1789. That possibility reveals a subtle bias in everything we observe. Planetary science studies survivors. Bodies shattered beyond recognition no longer present themselves as intact records. Their material may remain as fragments, rings, dust, or ingredients incorporated into later worlds. We therefore reconstruct destruction largely from what endured it. The solar system itself emerged through this sorting process. Early planetesimals, small bodies from which planets grew, collided repeatedly. Some impacts joined material together, others broke bodies apart. Over immense spans of time, surviving structures accumulated, changed, and sometimes collided again. The planets and moons we see today represent outcomes from countless paths that could have ended differently. Mimas sits unusually close to that boundary. Herschel Crater occupies an enormous fraction of its visible face, preserving evidence of an impact near the limits a small icy moon could withstand. What you see there is therefore more than damage. It is a physical record of persistence produced by circumstance. Life offers a different expression of the same broad pattern. Every organism alive today belongs to a lineage that passed through earlier environmental disruptions. Mass extinctions eliminated vast numbers of species, while surviving populations continued reproducing and changing. No guarantee carried those lineages forward. Their continuation depended upon conditions, variation, geography, chance, and biological traits meeting each crisis. We are descendants of those continuities. Mimas is the remnant of another. The comparison has limits because living evolution and planetary collisions operate through very different mechanisms, yet both remind us that existence leaves a selective record. We can examine what persisted because persistence made examination possible. Across the solar system, every surviving surface, orbit, moon, and lineage carries that simple condition within its history. There is no intention required. The pattern emerges from what remains. Beneath the outer ice of Mimas, sunlight becomes irrelevant. If the proposed ocean exists, its water lies under roughly 12 to 19 miles of frozen material. No direct sunlight reaches those depths. The energy shaping that environment comes from within, through tidal heating, pressure, and possible interactions between liquid water and rock. There, chemistry would proceed without seasons, weather, or photosynthesis. Reactions near the rocky interior could exchange minerals and dissolved compounds with the ocean. On Earth, comparable water and rock interactions can create chemical gradients, differences in available energy that microorganisms can exploit. Whether anything similar happens biologically inside Mimas remains unknown. The chemistry alone is remarkable enough. Its essential ingredient is deeply familiar. Water beneath Mimas would consist of the same molecules filling Earth's seas. Those molecules also circulate through clouds, rivers, plants, animals, and our own bodies. By mass, water makes up roughly 60% of an adult human body, although the proportion varies with age and physiology. Nearly every biological system we know depends upon it. This connection requires no symbolism. Water obeys the same physical laws on both worlds. Its molecules can freeze, melt, dissolve substances, transport chemicals, and participate in reactions wherever conditions permit. Location changes the environment around water, while its underlying molecular identity remains unchanged. Even its ancient history connects distant worlds. Scientists continue investigating how Earth acquired its water. Evidence suggests much was incorporated from water-rich material during the planet's formation, with additional contributions from impacting asteroids and perhaps some comets. Those reservoirs trace back to the protoplanetary disk, the rotating mixture of gas, dust, rock, and ice surrounding the young Sunday. Mimas also emerged from material belonging to that early solar system. So, when you consider water inside your body and possible water beneath Mimas, you are looking at matter whose histories ultimately reach into related primordial reservoirs. Individual molecules have been rearranged countless times since then, yet their ingredients were already present before Earth became the world we recognize. Today, Earth and Mimas can be separated by more than 1 billion miles. Their environments could hardly appear more different. One carries open oceans beneath an atmosphere and sunlight. The other may conceal liquid beneath a thick shell of ice, orbiting far from the Sunday. Yet distance does not create new chemistry from nothing. Hydrogen remains hydrogen. Oxygen remains oxygen. Joined as water, they form a substance familiar enough to drink and fundamental enough to reshape our understanding of distant moons. Perhaps that is the deeper perspective Mimas offers. When we search outward for environments unlike our own, we repeatedly encounter familiar ingredients arranged under unfamiliar conditions. A buried ocean around Saturn may therefore be alien in setting, while being composed of matter woven into our everyday existence. A scientific paper can begin with measurements almost too small to notice. In February of 2024, researchers writing in Nature presented evidence that Mimas may contain a young subsurface ocean. Their conclusion emerged from years of spacecraft observations, orbital calculations, and models of how the moon responds to Saturn's gravity. The result traveled far beyond the laboratory. Planetary scientists examined the methods, compared competing explanations, and debated what the measurements could support. Science publications carried the finding to a broader audience. Within weeks, a world once regarded mainly as a battered ball of ice had acquired another possible identity. Consider the chain required to make that possible. Cassini gathered information while operating hundreds of millions of miles from Earth. Radio signals crossed interplanetary space. Engineers received them through antennas on our planet. Researchers then transformed those measurements into estimates of motion, gravity, rotation, and internal structure. Eventually, patterns hidden inside the data became a scientific argument that people anywhere on Earth could read. We have built instruments capable of extending observation far beyond human senses. More remarkably, we have built methods for testing what those instruments tell us. Peer review, independent analysis, mathematical modeling, and future observations provide ways to challenge conclusions instead of simply accepting them. As far as we know, no other species has done this. Life on Earth has existed for billions of years, producing forests, reefs, predators, migrations, and intricate biological societies. Yet only one lineage has measured the rotational behavior of a distant moon and used that motion to infer buried liquid water. That ability brings us to an unusual boundary. Science can describe what the evidence supports. It cannot decide how strongly humanity should pursue the next measurement. We already know that Enceladus contains a global ocean and chemically rich material. Mimas may add another ocean environment to Saturn's collection, suggesting that hidden water can persist in places once dismissed as frozen and inactive. Yet, our reach remains limited. No spacecraft currently orbiting Saturn can inspect Mimas again. A probe designed to determine its internal structure would require years of development, a long interplanetary journey, and instruments sensitive enough to distinguish competing interior models. Reaching the ocean itself would be harder still. Roughly 12 to 19 miles of ice may separate the surface from liquid water. So we occupy a peculiar position. We possess enough knowledge to recognize the possibility, while lacking enough evidence to settle every question. For most of human existence, Mimas was beyond awareness altogether. Then it became a moving point of light. Later, it became a cratered world, photographed by machines. Now it may be an ocean world. Each change came because someone chose to look more carefully. Knowledge has carried us to this threshold. What lies beyond it depends upon where we decide to send our instruments, our attention, and our curiosity. At roughly 246 miles across, Mimas occupies almost no space on any cosmic map. It circles one planet around one ordinary star, inside a galaxy containing hundreds of billions of stars. Beyond the Milky Way lie galaxies. Beyond counting, against that scale, this little moon becomes almost impossibly small. Yet size has never determined scientific importance. Mimas carries evidence of a collision severe enough to reshape an entire hemisphere. Herschel Crater remains embedded in its ice, preserving the consequences of an ancient encounter. Its gravity reaches outward as well, influencing particles within Saturn's rings and helping maintain the Cassini division through orbital resonance. Even a moon this small can organize matter far beyond its surface. Then came the unexpected motion. Measurements from Cassini revealed a rotational wobble that could not be explained as easily as researchers expected. Years of analysis gradually changed the picture. In 2024, evidence published in Nature supported an extraordinary possibility. Beneath the cratered exterior, Mimas may contain a recently formed ocean. That possibility changed more than our description of one moon. For decades, the most convincing ocean worlds announced themselves through geological activity. Enceladus erupts material from its interior. Europa carries fractures and disrupted terrain across its icy shell. Mimas presents another possibility entirely. A world can appear ancient and inactive, while conditions deep inside have already changed. That realization alters where we look. Water may occupy environments whose surfaces offer few obvious clues. Internal heating can operate beneath landscapes that preserve scars from an earlier age. Chemistry may develop beneath ice long before geological changes become visible from space. The map of potentially habitable environments therefore becomes less dependent upon appearances. Most of what we now understand about Mimas entered human knowledge recently. William Herschel could detect only a distant point in 1789. Voyager revealed its extraordinary crater in 1980. Cassini transformed that photographed landscape into a measurable physical system. Modern analysis then carried us beneath a surface no spacecraft has penetrated, and there our knowledge stops. Somewhere below miles of ancient ice, liquid water may be moving around a rocky interior. Perhaps the models are correct. Perhaps future measurements will reveal another explanation. The distinction matters because science gains its strength from allowing uncertainty to remain where evidence remains incomplete. Mimas continues regardless. Saturn pulls upon it. The moon follows its orbit. Herschel Crater retains the geometry of an impact from another age. Whatever exists beneath the surface obeys physical laws, whether anyone measures them or not. But we have measured what we can. You now know the shape of a world you may never approach, the history preserved across its ice, and the possibility concealed beneath it. Across an enormous universe, one small moon became more understandable because human beings learned how to look. The map changed, and Mimas earned its place upon it.